Hello students, today we will discuss about the direct sequence spread spectrum communication technique. As discussed in the introductory module that direct sequence spread spectrum communication is one of the most popular spread spectrum communication technique. Other one is the frequency hopping spread spectrum, which we will discuss later on. Today we will discuss transceiver architecture, the signal model and the fundamental description of this direct sequence spread spectrum techniques in this module. Direct sequence spread spectrum system, as the name suggests, it is the signal model is obtained by the direct multiplication and direct mixing of this data with your spreading waveform. We understand that in the spread spectrum communications, the spread spectrum signal, it will have the extended waveform as compared to the data modulation bandwidth, and it will have an extended bandwidth also with respect to the underlined minimum required data modulation bandwidth. Here in the direct sequence spread spectrum system, the PN sequence or the spreading waveform will help us to extend the bandwidth of the spread spectrum signal as compared to the data modulated waveform. Before the final carrier modulation, we utilize this direct mixing of the data with the spreading waveform. As I have already discussed that in the baseband processing of the receiver, we have three different stages of the modulation technique. The first stage is the data modulation, where actually the raw data is modulated over is utilized to do the modulation of the carrier, and the famous techniques and the famous digital modulation techniques we utilize here is the BPSK, QPSK or the quadrature amplitude modulation or the QAM. And the modulation technique that I am referring in the spread spectrum communication is separate from the data modulation, and this is called the modulation due to spreading. And the final modulation apart from that is the carrier modulation or the RF carrier modulation that will be helping you to boost the signal from the baseband to the carrier to the RF carrier to the RF frequency, where the transmission will actually take care of. While this spreading will be considered, remember whenever we will talk about the modulation, this is after data modulation, but before the actual carrier modulation to the RF. So, coming to the mathematical model of the direct sequence spread spectrum signal, if we consider that the binary phase shift modulation keying is going on, it is and all or the differential phase shift keying is going on, then using the value of that dt to be utilized from the BPSK modulation technique will be utilized in conjunction with the spreading sequence PT to generate the spread signal ST. The A term here in this case will be the signal amplitude, dt is the data for modulation as I have told already, PT is the spreading waveform, FC is the carrier frequency, and theta will be the phase at t equal to 0, time instant t equal to 0. And remember the form of this dt, the data modulation that we are considering here for this analysis will be the BPSK. So, if we go to the next slide, we will be able to see the form of this dt here. The direct sequence, the BPSK modulation will be like this, where the incoming signal bit stream, if it is given as 0, 1, 1, 0, 1, 1, something like this. Actually, whenever the BPSK modulation is there, the incoming bit stream, the series of the zeros and 1 will be transmitted in the form of either +1 or -1 by the BPSK modulation. If it is a binary phase shift, then you will have a shift of plus minus 180 degree. corresponding to the incoming data bits. So, for 0 we will map the signal in the BPSK modulation as -1, and for +1 it will be transmitted as +1. So, for incoming signal, hence actually you will be able to see the way the modulated data is available now with us for spreading. If we with this understanding of this data part with us, we would like to go back to the equation where we were dealing with this data part. See, if this data is given by the PSK modulation, which is binary phase shift modulation, then this ST, hence we can write the ST as A PT cos 2 pi FCT plus theta plus this phase phi into dt. So, automatically the equation 1.1 can be also expressed in the form of this, with the concept that there is a PSK modulation is involved in the process. The spread waveform, how it will look like, we will come little bit later, but let us first concentrate inside how the PT, the spreading waveform, looks like. Remember, before entering into the PT, I would like to mention here the symbol time of the data we will mention here as Ts. The PT, which is the spreading waveform, is usually given by the equation minus infinity to plus infinity pi psi t minus ITC, where psi is taking care of the chip waveform and pi is either equal to +1 or -1, and it represents the chip of the spreading sequence pi. What is the form of a chip? So, here we are not talking about a bit. Here in the data case we will be talking about a bit, and per bit duration we will have the multiple number of the chips, because there is a relative relation between the chip duration and the symbol duration in the space spectrum communication. Coming back to the concept of this waveform, chip waveform and the spreading waveform PT, we are seeing here the PT is also designed in such a fashion that the values the chip that can take is either +1 or -1 over a duration of the chip. The chip duration we will consider as Tc. The waveform that PT, the psi t, can take care of is usually the most common kind of the waveform is the rectangular chip waveform given by the Wt by Tc, and this rectangular waveform is defined as 1 if the time period is within 0 to the maximum period of capital T, and it will be 0 otherwise. The figure here in figure 1, the spreading waveform is shown for the rectangular chip only. So, there are two questions coming in between, because one is the relation between this Ts and Tc. What is the meaning coming out from here? See, within the T whole duration of that symbol duration of the Ts, as Tc is designed intentionally to be much lesser than my Ts, as Tc is designed much lesser than Ts, and this is my Ts and this was my Tc. So, hence if I divide Ts by Tc, I will be ending up with certain integer number. To get to the integer number, we usually try to keep one assumption that whenever the transition is happening for the data symbol and the chip symbol, they will be in sync on both the direction, on the both the side of the data. So, if this is maintained, that they will be in transition will be in sync for both the PAC, PT and DT, then definitely you will get the integer number of the chips involved inside the Ts. This n, the number n, Ts by Tc, is a very important parameter in the space spectrum communication design. We call it usually the processing gain. and this is involved, this is usually mentioned by the term G. It says actually within the number, within the symbol duration, how many number of the chips you are designing for transmission. Basically, actually the 1 bit data is actually now spread over these many number of the chips, capital N number of the chips. In terms of the bandwidth, if you wish to understand, because we are playing with the, fundamentally we are playing with the bandwidth, and the name suggests that we are expected to get an extended bandwidth. So, let us see how is it happening. Once I am actually multiplying the dt with pt as the signal model previously show here in equation 1, that the spread signal will be obtained by the multiplication of the dt with pt. So, once I am multiplying these two waveform dt with pt, then at the end of this multiplication I will be ending up with the chips only, there will not be any existence of the bit. So, when we are ending up with the chip, so there will be, instead of the bit rate, the transmitted signal will be talking in the terms of the chip rate, and as the chip is involved, so after multiplication, that means after spreading, you will be able to see this Tc. So, as Tc is much less than Ts, if I consider that the corresponding bandwidth of this Tc is given by W, and the bandwidth of the data modulation corresponding to Ts is given by B, definitely B is equal to 1 by Ts and your W is equal to my 1 by Tc, then easily I can see that the after multiplication, when I am ending up with Tc, I will be governed by the bandwidth W, hence the spread spectrum signal bandwidth is becoming W. Which was earlier the bit bandwidth was signal bandwidth was earlier B, whereas as Tc is much less than Ts. So, obviously, my W will be much greater than the B. So, earlier when without spreading you were requiring a bandwidth of B to transmit the data signal dt, now you require a bandwidth of capital W to transmit the spread signal dt into pt. So, that is why we tell the name as spread spectrum communications. We intentionally spread the data bandwidth of the data modulation than the minimum required bandwidth, and we have there is a processing gain involved in the whole process. Why do we wish to do all that? As indicated in the module 1, that this kind of communication ensures the message privacy or the message secrecy, and we wish to get the resilient against the interference or the jamming signal. This kind of the spreading of the waveform we will see a little bit later in a pictorial form, the way the bandwidth is expanding after the spread spectrum communication, and how in the receiver we are processing the signal such that we are getting the good resilience against any kind of the narrowband interference or the narrowband jamming. Another point, in order to have the message privacy or message secrecy, the assumption of perfect alignment of the transition of the PT and the DT is really very valid terms. So, we will consider throughout the explanation and description that there is a perfect transition match between our DT and PT. This is the conceptual block diagram of generating the spread spectrum signal in the transmitter, where the direct sequence transmitter is utilizing the PSK, either binary phase shift keying or the differential phase shift keying. The data symbols and the spreading sequences, both, in order to bring them in sync, we actually drive both the circuit by the same clock. Here we are having a data generated block which is generating the data symbols zeros and ones. So, clock will be driving both the data generator and the spreading sequence generator at the same time, and these are added in this block, and before actually the chip modulation, chip waveform modulation, they are added together, and finally, this is a oscillator. This is the modulo to addition going on inside it to give the effect of equivalent effect of the multiplication of dt with pt. The output of this adder actually will be converted by this -1, 0 to -1, and 1 for bit number 1 to +1. If the coming bit is 0, we will get -1, and the incoming bit is 1, we will actually get +1. Then the bits, then the waveform is having a chip modulation, and finally, here is the carrier modulation going on. See, in the practical circuit, we add the wideband filter here, power amplifiers, and add wideband filters before transmitting the signal from here. Here is the ST that we have already shown you earlier, which governed by A, PT, dt, cos 2 pi FCT plus theta. The signal we have generated earlier is getting transmitted. But before that, we have to pass it through a power amplifier to boost up the power level, because the signal is expected to traverse a long distance over the wireless communication channel, and the wideband filter is utilized to cut out the unwanted signal portion of the spectrum out of the band of our interest. Usually what happens in the practical communication system is whenever you are you have started with a nice rectangular chip waveform, right, but once this chip waveform is passed through a wideband filter or through the wireless communication channel, both the filter as well as the channel, they disperse the signal and the waveform gets changed like this. So, the fundamental effect that we see is that there is a spillover because of the dispersion of the filter as well as the wireless communication channel. There will be a spillover of the power of say t is equal to 0th pulse over the t is equal to 1th pulse. The effect that we are considering here is we call it as an chip interference. So, there is a interference from the previous chip to the next chip as if, and we need to take care of the nice filter design inside the transmitter, so that actually this effect can be nullified. So, thing is we considered earlier that the chip is designed such a way, the rectangular chips are designed in such a way that it will be confined within the duration of the 0 to Tc, and there will be a nice transition which is in sync with the data. Now, that concept or that theoretical concept will be disturbed by the presence of this wideband filter as well as the wireless communication channel. So, the pulse design that I was mentioning, that we have to take care of, and we have to design the pulse in such a way that it satisfies the Nyquist criteria that confirms that there won't be any inter-symbol interference or inter-chip interference in this situation in between the transmitted symbols. So, hence once it is received, there won't be any effect of the inter-chip interference or the inter-symbol interference. We will discuss little bit here about what exactly is this inter-symbol interference effect, how can you design the Nyquist pulse. The Nyquist criteria is like this. Nyquist thought that in the first criteria, Nyquist designed a pulse in such a way that the pulse will have equal to, the value will be equal to 1 when t is equal to 0, and it will have the value 0 for any other t is equal to say n into Tb, where Tb is the duration of the pulse. If I map it into our case, then we need a pulse where the value will be equal to 1 at t equal to 0, and its value will be exactly equal to 0 when t is equal to n into Tc. How the pulse will look like then? The pulse will look like this. We call it a sync pulse. The other pulses are, the replica of the pulses are going like this. So, you are getting a peak value when others are, its corresponding pulses are not having any peak. Okay. So, the pulse that we are Nyquist took, and these are the one places where actually it is minus TB and this is plus TB. So, this is twice the TB value, this is minus twice TB value, and TB is equal to 1 by TB, we will call the bit rate RB. So, if you design a pulse like this, it can be shown that you can transmit the data RB amount of the data using a bandwidth. The theoretical minimum bandwidth required is equal to RB by 2 in that such situation. But question is that it is really very hard to maintain the bandwidth of within RB by 2. Usually we see that this first criteria, Nyquist first pulse design criteria needs some excess bandwidth. So, what we try to do is we Nyquist came up with a second kind of the pulse design, where he showed that the bandwidth further, if we wish to reduce, we can simply do it by increasing the distance, increasing the width of the pulse. So, that the width of the pulse that we are now talking about will be given by this. So, now we will be having the two different situation, two different values of the t, for which the pulse will have the high value is equal to 1, and this is t is equal to 0 and say t is equal to 1. For both the cases, the pulse will have at least show the value equal to 1, and hence it we call it the controlled with controlled interference. We can have we can design the pulse, the transmitted pulse. But here remember, when we are having the controlled interference, why I am saying it is a controlled interference, because for t is equal to 0 the interference may be 0, but for t is equal to 1 you have some interference from the next pulse. But that is the pattern is will be well known, and it is a criteria of the pulse design of the Nyquist pulse design criteria involved, where actually it will help you to control the ISI or the inter-chip interference in our case to a great extent. So, before transmitting or releasing the spread spectrum waveform in the air, after power amplifier and the wideband filtration operation, we have to also take care of this pulse shaping. With proper shaping of the pulse only to control the intersymbol interference in the receiver, we will release it in the air. Now, with this understanding that now hence if there is a spillover of the pulse over the duration of the TC, then hence the direct sequence signal should not look like the way we have written it earlier. Now, the sequence will look like this, where actually this part is talking about the integer part of this x, I by g is the integer part of this x. This symbol is indicating the integer part of the element which is inside it, and how actually this I can go from this minus infinity to plus infinity, depending upon the dispersion it has happened to the effect of this signal with the intersymbol interference. The chip waveform will look like this, and the data part is not now actually typically in the receiver, you won't get the data received typically for that instant, and the transmitted signal is definitely getting reformed by this spilled over signal. If we look into the receiver sector, the receiver functional block diagram conceptually will be looking like this. So, there you are sending the data after the wideband filter, and here at the front end you need a wideband filter to capture the signal of your interest. With the filter center frequency will be the center frequency of the transmitted one, that is equal to FC. And after extracting the synchronization information, and the synchronized locally generated spreading waveform is utilized to dispread the incoming signal. So, here we utilize again multiplier, which multiplies the incoming received spread signal, and once this multiplication is done, we are here receiving the disparate signal. The operation, this operation where we multiply the locally generated PN sequence, which is exactly known a priori sequence that was used in the transmitter, with the incoming spread signal, we call this process the disparing. the apart from the output of the spreading, out of the spreading block, the signal is entering into the PSK demodulator, which will demodulate the signal later on. But remember one thing, as actually the PT what we were generating is basically will be again the rectangular waveform. If we use a rectangular waveform in the transmitter, hence the value of the PT will be +1 -1, and once we are multiplying this, we will be ending up with the p square t, which will be always giving you the value of the 1. So, at the end of this despreading process, you will be ending up with the signal A into dt multiplied with this carrier frequency cos 2 pi fct plus theta. The disparate operation what we have understood here in the mathematical form, it will be good now to see that how pictorially spectral wise it will look like. Remember, so in the transmitter what we did, we spread the signal, because we understood that dt into pt will spread the signal, because it will be governed by the bandwidth of pt, because the tc is very less for pt. So, bandwidth was high, and hence actually the signal bandwidth was spread over w now. Okay. It was a spread signal. And interference, who actually does not know what exactly the sequence you have utilized, the sequence is a key secret key for you. So, interference will be of a narrow band interference having a bandwidth lower than the spread bandwidth. When you have received the signal, you have received the signal combined with the interference, who is having the spectrum orientation like this. Now, inside, so this W by B is taking care of the fact how good we will be in rejection of the interference. More actually the ratio will be, more actually the gain will be, and more you will be the resilient against the interference. In the receiver, after disparate operation, what will happen? After disparting, the signal bandwidth will again contract. Will again they will be compressed over the bandwidth of where from we started with. But as now the interference is getting multiplied with the locally generated PT, which was not done earlier, hence PT will help this interference to spread over the bandwidth W. Remember one thing, as we are considering the gain bandwidth product of the whole design is constant. So, when you are increasing the bandwidth, the gain of the signal is expected to come down. So, when we expanded the transmitter signal in the transmitter over the bandwidth, see the bandwidth the power was reduced, it was spread over the whole bandwidth. Once you have compressed the signal in the receiver after dispreading, your bandwidth has squeezed and the signal power has come back. And it is not the back, it will be even higher than the transmitted signal power, because you will be having a power gain also by the term of this processing gain G. Here actually in the case, the thing is opposite in case of your interference. Now, they have got spread over a bandwidth of W. So, whatever the power with which they transmitted, now it has come down to a very low level. So, it will be equivalent to the noise, it cannot, its power is very much low compared to the signal power, which has already got boosted up, and it will be easy for us now to detect the signal in presence of this interference power. So, that is the beauty of this kind of space spectrum communication. You are getting resilience in presence of the interference, and you can actually very nicely detect your own signal in presence of the interference. And the easiest way of this modulation technique is to replace and to go ahead with the correlator architecture, which is basically the match filter plus the correlator architecture that we will discuss in detail in the later module. And this is the more easiest way, the way we can implement in practice the match filter based and the correlator match filter and the correlator based demodulated circuit for the space spectrum communication system. This is the optimum demodulator in the form of this correlator circuit, where actually the detection of the signal in the presence of the wide Gaussian noise can be possible. This correlator is very, as I told, it is a more practical and the flexible for the digital signal processing, and though the whole design is suboptimal, but it is a reasonable approach against any kind of the non-Gaussian interference. We will go ahead with the next analysis of the direct sequence space spectrum system based on this architecture, receiver architecture. Remember, whatever the initial two figure conceptual block diagram figures we have shown, we excluded the power amplifier in the transmitter, and we also excluded the automatic gain control sector in the receiver. Understanding the fact that such devices are not having any significant effect on the demodulation operation. So, we will be proceeding with those algorithms, but in practice we will have all those RF circuitry involved in front of that baseband module that is shown in figure 2 and 3. And in figure 5 also, going by the same effect, we have omitted the front end independent blocks like your wideband filter followed by the low noise amplifier and the automatic gain control. We will give more thirst on the demodulator circuitry, optimum demodulator circuitry, which is designed here in the form of a correlator for the detection of this symbol in the presence of wide Gaussian noise. And the equivalent match filter demodulator will be is actually basically it is implemented in practice by means of tap delay line or the transversal filter, and the stored spreading sequence is also utilized for the online or offline processing of the spreading in the receiver circuitry. So, in the next module we will continue with the architecture designed architecture already mentioned in the figure 5 in detail to do the performance analysis of direct sequence space spectrum systems.